Then today, inshallah, we try to talk about the relation or the connection between derivative and integration. In one word, the integration is the antiderivative. That means the inverse action related to the derivative. That means today we will study, inshallah, some fundamental theorem of calculus when we have a connection between two branches of calculus, differential calculus and integral calculus. بمعنى نحاول نربط بين التفاضل والتكامل if we want, or the relation between derivative or differentiability and integration or antiderivative. في بعض الناس يسموه حتى antiderivative بمعنى الأكشن inverse related to the derivative. Then in order to do this, we introduce this function. We know when f is continuous, this function is defined integral between a and x f of t dt. Why? Because we said f is integrable because f is continuous, and in this case, g of x is well defined. We don't have any problem. And when we draw the graph of the function f, the blue area is g of x. When we change x, we have to move this vertical line because now we are in the level x. We have just 1 minute. Okay. Then the vertical x move, this line move. When we change x, we have to move this line. When we move this line, obviously the area change a little bit. When we move x a little bit, the area change a little bit. Then x equals a, this line is fixed. However, since we have a function related to the variable x, then this line, this vertical line move, when we change x, that means we move this. As application, this is a function, okay? And the requested here, find the values of g of 0. What about g of 0? What about g of 1, g of 2, g of 3, and g of 4? The requested is g of 0 first. What about g of 0? When we look, this is the function. We don't have any idea about the function. We know just the graph of the function. It's like that. And what is g of 0? G of 0 is this area, because we have to start in 0. I'm sorry. I want this area, the area between x equals 0, x equal 1, the graph of the function and the x-axis. Then this is g of 0. G of 0 is this area. Is it possible to evaluate this area? When we have a triangle, is it possible to evaluate it? Yes, the answer is the first side times the second side divided by 2, because this area is the half of this rectangle. The area of the triangle is equal to the half of this rectangle. Okay, the area of the rectangle is one side times the others, 2 times 1. However, the area of the triangle is the half of this. That's why first, just a comment here, just an observation. G of 0 is equal to 0. What is the meaning of G of 0? That means we start in 0 and the end point is 0. Then the integral between 0 and 0 of any function is equal to 0. When the start is the end point, then the integral is equal to 0. For g of 1, it's the integral of the first picture. Then, as I said, it's the area of the triangle, which is equal to 1. What about g of 2? Okay. G of 2 is the area of the triangle plus the rectangle. Why? Because it's what we have to do. We have to evaluate the area when this is one side. This is another side because we finish at 2. This is the third side. And for the last side is the graph of the function. Then we try to draw this area, to evaluate this area. This area is equal what? When we look here, we can see this area is equal the area of the triangle plus the area of the rectangle, which that means, or we can use the formula. The formula studied before is integral between a and b f of t dt is equal, remember, integral between between a and b f of t dt is equal what? We can introduce any point between a and b. Okay, it's equal integral between a and c plus integral between c and b. Okay, then what we introduce, we add the points. Okay, we start in a, we finish in c, then we start in the same point c, and we finish in the b. Okay, this is obviously here we have to write f of t dt. Here, this is f of t dt, and this is f of t dt. This formula was studied before, and that's why when we apply this formula, the integral between 0 and 2 is equal to the integral between 0 and 1 plus the integral between 1 and 2. The integral between 0 and 1 was evaluated before. It's equal g of 1, which is equal 1. Okay, that's why this area is equal 1. It was evaluated before, it's this area. Okay, it was evaluated when we evaluate the expression of g of 1. Now, I want the integral between 1 and 2. What about the integral between 1 and 2? What is the graph here? Between 1 and 2, what is the area? The area is the area of this rectangle. Why? Because we start in 1, we finish in 2, this is the x-axis, and this is the graph of the function. Then obviously, we have to evaluate this expression. One side times the other, which is equal 1 times 2, 2, plus 1, plus the first integral, which is equal, is it clear? Okay, لأنه الفانكشن defined like that. إذا كان الفانكشن تتغير، إذا هنا مثلا طبعا تصبح function more delicate when it becomes more hard when we change instead of x, 0 x over 2. If, for example, we do this, it's another thing. And here we have to, because what I have to do, I have to substitute in this expression x by 1, by 2, by what I want. X is just here, okay? That's why only this line, this vertical line change, okay? ما يتغير إلا الإكس لما ننظر للإكسبريشن هنا الإكس موجود إلا up إلا هنا بس، okay? That's why. اوكي اذا كان موجود في اماكن ثانيه تتغير اشياء ثانيه، بس كله دائما مهما كانت الاكس وانا I have to evaluate g of 5 I have just to substitute x by 5 نعوض الاكس بال5 بمعنى دائما نبدا من الزيرو. واضح؟ اذا كان الحد الاسفل هذا اللي في البوتم هي اذا كان depends of x اذا يتغير، بس in this case we start in 0. Okay. Okay. When we start in 0, 0 is fixed. However, when we from 0 to x, when x change, this integral change, but we start anyway in 0.
Okay. Right.
Once again, we start in 0. Further, it's okay.
Okay.
When we try to evaluate g of 3, once again it's equal. We go back to your expression and we put x equals 3 here. It becomes integral between 0 and 3, but 0 and 3 I divide it in 2 parts. It's equal between 0 and 2, which was evaluated before, which is equal 3, plus between 2 and 3. Between 2 and 3 I don't have the exact value. However, I can see it's a little bit more than 1 because when I join this point, the blue area here between 2 and 3 is more than 1. However, obviously it's less than 3. طبعا الجزء هذا نقول ثلث المساحة المثلث الباقي That's why it's 30%. It's just an approximation. As you look here, it's around 0.3. Okay, when this is the area of the triangle, here we take just the blue part is just 0.3, just 30% of this area. It's just an approximation. تقريبا 0.3 من المثلث الأعلى هو اللي ملون. That's why he said 1.3. But it's not exact value, it's just an approximation. And it's like that. When we add 3 plus 1.3, it becomes 4.3. Now, I try to evaluate G of 4. For G of 4, once again, I have to evaluate between 0 and 3. It was done before, plus this integral. However, be careful here. The function becomes negative. Since the function becomes negative, then I have to evaluate this area, then and subtract it. Why? Because it's negative. Okay. Then this area is, we have the same area. This area is like the blue part between 2 and 3. That's why in terms of area, it's equal 1.3. Then I have to subtract 1.3, which becomes 3. Finally, I have to evaluate G of 5. G of 5 is equal. I can do it like that. I start from 0 to 4, which was evaluated before, and it's which equal 3, plus this integral. But this integral is negative. It's equal minus this area because we are down the x-axis. Since it's negative, then it's equal 1.3. We have symmetry. That means in terms of size, this area is equal this area. The left side of this line, this black line, is equal the right side. We have symmetry for this area. Then in terms of size, it's equal 1.3. Then 3 minus 1 over 3, 1.3, which is equal 1.7. Obviously, this is a particular function and the particular points. Okay. However, we can see the following. We can look when we start in 0, when we move x between 0 and 3, your function is increasing. Why? Because we add, look here, when we choose the 1 point and another one. What is the difference? When we move in the right, we add this area. That means we have an increasing function. كل ما نكبر في الx لحد 3 كل ما المساحة تزود تكبر لأنه all is positive لأنه my function is positive. However, when we when x equal 3 and we move to the right, the area becomes decreasing. Why? Because we are going to add something negative, that means to subtract. That's why my area is decreasing. Okay. Obviously, thanks to some software, we can obtain this function. Then this is a general observation. Okay, that means when I have G, define it thanks to the function f, and I have the graph of the function f, I can have an idea about my function. This is a G of 1, because I know G of 0 is equal 0, G of 1 is equal 1, G of 2 is like that, G of 3 is like that, and G of 4 is like that. I evaluated all of these points. بمعنى النقاط هذه كلها معي. طبعا نحاول نربط الرسمة, and we know 3 is the maximum because when we are in the left of 3, the function is decreasing. However, when we are in the right of 3, the function is decreasing. That's why we have something like that. This is my first observation. When we change the function, this one is not important, but the main important point is here. Here, when what is the relation between G and F? The question, an important question is what is the relation when G of x is equal integral between a and x f of t dt? What is the relation between G and F? The answer is the following. G prime of x, when we evaluate the derivative of the left side, it's equal f of x. Be careful, this is an important formula. And we can we have a relation between g of x, the function evaluated, that means here when we, this is the function, the graph of the function f, and this is the graph of the function g, which is the integral between 0 and x, in this case, f of t dt. Then we have a relation. When we evaluate the derivative of g, it's equal f. That's why when f is positive, your function is increasing, and when f is negative, your function is the function g is decreasing. Then we have a connection between g and f. When f is positive, g is increasing. When f is negative, g is decreasing, and we have more. That means the derivative of g is equal f. Then this is an important point. That's why in sometimes we said this action, this integration is anti-derivative. That means the inverse action of the derivative. بمعنى الحركة العكسية زي ما تقول ذهاب وعودة. When one direction is the derivation, the other one is well, in order to go back, we have to apply the integration. Then the integration is the antiderivative or the inverse fraction, the inverse action related to the derivative. I did this one. Now I'm in slide 13 maybe. Then this is the important part. As application, I want the derivative of g. What is the derivative of this function? The derivative of this function, it's integral between one fixed point and x. Be careful. It's between one point fixed 0 and x. Okay, when we have 2x, the situation is different. But be careful when it's between 0 and x, a function, then the derivative is equal the function inside the integral. Then the derivative is equal, the derivative of my function is equal root 1 plus x squared. That means this function in the point x. Okay, بمعنى في البراكتس اشتقاق الدالة جي هو الدالة اللي داخل الانتجرال بس نعوض التي بالاكس. This is all. This is thanks to fundamental theorem of calculus. Okay. Obviously, when my function is continuous, g is differentiable. Okay. When my function is continuous, the derivative is my function is differentiable. That means I can evaluate its derivative. This one is not very important, but I'm going to talk about this one. We'll talk about it later with more details. But my question, when instead of x, we have x to the 4 here, what is the difference here? Here we don't have x, we have x to the 4. Okay, we have the integral between 1 and x to the 4. Be careful, it's not x. When let capital F of x is equal integral between 1 and x sec t dt. What I can see, sec t dt. If this integral is equal sec t dt. Okay, sec t dt. What is the relation between this function and the function capital F? It's equal. Then when I want to evaluate the derivative, it's equal the derivative of the function. I have to take f not in the point x, but in the point x to the 4. I don't have to take the function f, capital F in the point x. I have to take it in the point x to the 4. Why? Because it's integral between 1 and x to the 4. Then it's a composition between this function, defined here, capital F, and the function x to the 4. That's why its derivative is f prime, thanks to the chain rule studied in chapter 2 and chapter 3. F prime in the same point, in the parentheses we have x to the 4 times the derivative of x to the 4. What is the derivative of x to the 4? The derivative of x to the 4 is equal 4x to the 3. Obviously, now the derivative of capital F, when I talk about this function, its derivative is equal what? F prime is equal what? F prime of x is equal sec x. Why? Because it's integral between 1 and x in this time. When I talked about capital F, it's integral between 1 and x. That's why its derivative is sec x. I don't have any problem. What about the derivative in the point x to the 4? It's equal sec in the point x to the 4. Sec, but not in x in the point x to the 4. But be careful, we have to multiply it by 4x to the 4. 4x to the 4. Just we will talk about this kind of problem later when we have instead of x here, when we have instead of x another function, what is the derivative? In this case, the strategy is like that. We assume capital F of x is equal the integral between 1 and x, and we know its derivative is just the function inside the insider function. But we have a composite function, that means it's a composition between f, capital F, and x to the 4. That's why the derivative, thanks to the chain rule, the derivative is equal the derivative of the function capital F in the point x to the 4 times the derivative of x to the 4. The derivative of the function is the sec x in the point x to the 4 times 4x squared. Obviously, this is the result. Now we are going to look another important theorem, which called the one fundamental theorem, which is integral between a and b. Remember, in my first example, I have to evaluate integral between f of x dx. The answer is the following. If we know some capital function such that its derivative is small f, then this expression is equal f of b minus f of b, f of b minus f of a. We have some notation like that. We write f of x, which is by definition f of x between a and b. That means we take the value in b, I'm sorry, minus the value in a. It's just a notation. When we have this notation, f of x between a in the bottom and b up, between a and b is equal f of b minus f. Then this theorem is very important because he said, in order to evaluate this integral, I need capital F. What is capital F? Capital F is a function such that its derivative is f. Just a fixed idea. If f of t is equal to t, what about capital F? لما f paradigm, assume in the particular case, if f of t equal t, what is capital F? I want a function such that its derivative is t. What is f of t? هي أي دالة لما نشتقها نجد تي. مين عنده فكرة على الدالة هذه؟ حتكون إيه يا شباب؟ حتكون دالة أسية ولا بولينوميال ولا كوساين ولا ساين ولا مين مع الدالة لما نشتقها نجد تي؟ لما نشتق الكوساين نجد تي؟ طبعا لا. بس لما نشتق تي تربيع نجد إيش؟ لما نشتق تي تربيع. When we evaluate the derivative of t squared, we obtain 2t. That's why we have just to divide by 2. Because the derivative of t squared divided by 2 is equal 2t divided by 2, which is equal to. That's why, even a good question here, when we have small f, I want capital F. Capital F is a function such that its derivative is small f. Why small f is acceptable? Because I have to check. What that means, I have to check. I have to evaluate its derivative. Its derivative is t. That's why it works. Then to know capital F is a good function or not, I have to evaluate its derivative. Its derivative is t, then it works. Get clear? Obviously, this is related to this particular case. Then to summarize what is calculus in one word, calculus is differentiation and anti-differentiation or integration, because integration is the inverse process of differentiation. Okay. Then here we have all useful information just to remember. Here, this in slide 21, we have the information requested. The first one is g of x is equal. If g of x is like that, then its derivative is small f. And when we have integral between a and b, it's equal capital F of b minus capital F of a. What is f? What is capital F? Capital F is a function such that its derivative is small f. Okay, now need to do the proof. I have just two examples. What about the integral? Remember, we said in the first section, the integral between 0 and 1, we used some computation, and we said between 0 and 1 of x squared dx, we said this integral, thanks to some summation, it's something like 0.3. Remember, we said it's something like 0.33. Okay. The question, what is the exact value? The answer now is very easy. Why? Because I want just a function such that its derivative is x تربيع, is x squared. فلأنه من يديني دالة لما اشتقها x تربيع. إيه الدالة؟ The function is x to the 3 divided by 3. Why? Because when we evaluate the derivative of this function, لما نشتق الدالة هذا نجد كم شباب؟ x to the 3 divided by 3. When we evaluate its derivative, it becomes x squared. That's why if f is x squared, capital F is x to the 3 over. Then we take the value in 1 minus the value in 0. بمعنى هي نعوض الاكس بال1 minus نعوض الاكس بال0 which 1 over 3. طبعا الكلام هذا قلناه قبل، قلنا انه الانتجرال between 0 and 1 x squared is equal 1 over 3. But now we said as approximation, but now we know why it's exactly equal 1 over 3. The last application in this section is the following. I want to evaluate, then it's very important to know the antiderivative. بمعنى it's very important to know when we have a function what is its antiderivative. That means if we know small f, what is capital F? For example, just I think you know this. When I write what is when f of x is equal x to the 3. What is capital F? Capital F, what is capital F? Capital F is a function. I want what is capital F. What is capital F? Capital F is a function such that its derivative f prime is equal x to the 3. أبغى الدالة لما اشتقها نجد x to the 3. مين مع الدالة؟ لما نشتقها نجد x to the 3. في البراكتس okay, f of x is equal what? Is equal 1 over 4. بمعنى ناخذ الأس نزوده واحد 1 over 4 x to the 4. ليه؟ لأنه لما نشتق هذا try to evaluate the derivative we obtain x to the 3. More general نديكم قانون لما f of x equal x أس alpha, be careful, alpha not equal minus 1, f of x equals x to the alpha, alpha not equal minus 1, be careful because I'm going to talk about minus 1, alpha not equals negative 1. Then a capital f of x is equal نزود 1 في الباور ونقسم على الباور الجديد. It's equal x alpha plus 1 divided by alpha plus 1. طبعا زي ما تلاحظوا يمكن نقسم على alpha plus 1 لما alpha تكون not equal minus 1 لأنه هذا ما هو زيرو. What about if f of x equal 1 over x? If f of x equal 1 over x is equal 1 over x, then capital F is equal ln absolute value of x. Then capital F of x, this is the منطق القانونين هذوما مفيدين كثير. f of x is equal ln absolute value of x. Why? Because when we evaluate its derivative, it becomes 1 over x. الإجابة ليه like that؟ لأنه لما تشتق الكابيتال F تجد small f بس بكل بساطة. بمعنى يلزم هي الحركة العكسية للاستقامة. Is it clear? Then I have to go back to my... Then that's why here when we have 1 over x نحتاج capital F. قلنا capital F هي ln x. ناخذ ln x. طبعا we have to evaluate between 3 and 6. Then x is positive. No need to put absolute value لأنه absolute value of x equal x. إذا ln x between 6 and 3. نعوض ln x بال6 بعدين minus ln x بال3. طبعا it's a property related to ln b minus ln a is equal ln b over a. 6 over 3 is ln 2. This is all for today for this section.